Hey, welcome back, everybody. The exam is still in the process of being graded, at least graded for the ones that I need to grade. So I should have those completed by tonight. So far, the ones I've seen, they look pretty good so far. No major problems that I can see. Anyway, any questions at this time? Yeah. All right, I will continue with the slide that we ended with, which was slide 16. Here we are talking about the chemical bonds, and we talked about ionic bonds and covalent/molecular bonds, okay? The main thing to remember about that is that ionic bonds consist of a combination of a metal and a nonmetal, and covalent bonds consist of a combination of two nonmetals. Okay? And that's important to recognize that. And so you need to go and refresh your memory with respect to the periodic table and find out the elements, who's a metal, who's a nonmetal. How do I go about determining that? Use the stair step of the periodic table. Anything to the left of that stair step are nonmetals, are metals, with the exception of hydrogen. I can't overemphasize that because I see that listed as a metal all the time because it's to the left of the stair step, okay? And remember, that's not the case. Now, where to go? Bear with me 1 second. Yeah. All right, there's that stair step underneath boron, okay? To the left is our metals, and except hydrogen. Hydrogen is group 1, element number 1, that is a nonmetal. And then to the right of the stair step are the nonmetals, okay? So once you determine that, that tells you what kind of chemical bond your compound has, whether it's ionic, whether it's covalent. The thing about ionic compounds, they're not a true bond. They are electrostatic attraction between a positive and a negative ion, okay? Much like two magnets coming together. There's no sharing of electrons. The other aspect about ionic compounds is that when you place them in a solution, specifically an aqueous solution, they will dissociate into the respective ions. Now, some dissociate 100%, some dissociate much, much less. Nevertheless, all ionic compounds do show some dissociation in water. That's the property of ionic compounds. The counter to that is the covalent compounds. In that scenario, we have two nonmetals that are bonded together, physically sharing electrons. And we're going to talk about equal sharing and unequal sharing down the road. Okay. The other aspect about that is that when I put those covalent bonded molecules in water, they do not dissociate into ions. Only one exception, and those are acids. And we have a whole chapter on that, but that is the only exception of a covalent compound that will dissociate in an aqueous solution. Okay. All right, so we talked about H2S, whether these are shared or not. We went through that scenario. And basically, we also talked about the energy involved of breaking and forming bonds, whether you're losing energy or gaining energy, either giving you either a endothermic process, meaning that it requires energy from the environment and thus gets cold, or an exothermic process, which gives off heat and therefore gets warm. So an exothermic reaction, for example, versus an endothermic reaction. All right. Now, this brings us to what we call Lewis dot structures for atoms. Now, this is only true for those elements are in the A elements. So that's groups 1A through 8A, okay? So finding their position on our periodic table, we know how many valence electrons they have. With that information, then we can draw what are called the Lewis dot structures, which is just basically an image of or the symbol, and then a dot that represents how many electrons. For example, we can take sodium, find sodium, it's in group 1A, okay, which means there's one valence electron, so we simply do a dot, and we're good, okay? That is the Lewis dot structure for sodium. All right, let's try carbon. Okay, carbon's here. And we know that find its position on our periodic table. It is in group 4, okay? Group 4A, which tells us there are 4 valence electrons, okay? Where sodium was in group 1A, which is 1 valence electron. And with 4 valence electrons, we simply put 4 dots around the symbol as follows, okay? That is the format of the Lewis dot structure. Now, think of that format. Let me talk briefly about that format. Think of the format as a box, okay? That box represents the symbol of the element, okay? So it's an imaginary line here. Now, when we add electrons, we simply go around the symbol. So like in carbon, we went to the top of the box and then to the side and then to the bottom and to the left side. This is basically just demonstrating how we put electrons, the valence electrons, in specific orbits, okay? Now, if we went around and had a group 5 electron, let's say nitrogen, nitrogen's in group 5A, and it has 5 valence electrons. Well, we go around the horn, so to speak, right? Go around 1, 2, 3, 4, and then the 5th one goes any place here. Now, whether I start on top of the box, to the side of the box, makes no difference, okay? Start any side of the box that you want. Just put your electrons on there. When the sides, the 4 sides are full, then we continue to go around. There's 2 dots per side until we fill it up and we get to, let's say, argon. Argon is in group 8A, right? So that tells us that we have 8 valence electrons. So to draw that structure, we just go 1, 2, 3, 4, 5, 6, 7, and 8. So at that time, we start filling up more electrons. We go all the way around the horn, so to speak, 2 electrons per side, and we're at the octet. Okay, so that is the format. Think of the element, the symbol as a box, and just go around it. Whether I go clockwise, counterclockwise, whether I start at the top, on the side, bottom, it makes no difference. Start whichever side you want. Go clockwise, go counterclockwise. That's fine. The important part to take away from here is that you can find the number of valence electrons, and then from that information, draw the Lewis dot structure for the atoms. We're going to be using that information, the Lewis dot and the valence electrons, when we start putting structures together and figuring out the geometry. We're going to need to know how many valence electrons every element brings to the table, okay? Because that tells us how the structure is put together. All right, so let me clear the table here. So group number, as we just talked about, identifies the number of valence electrons, and then we just simply start from one side of the box, if you will, and go around the horn. Start top, bottom, left, or right, whichever works for you. And in this case, they're asking you to do the Lewis dot structure for potassium, oxygen, silicon, and magnesium, and iodine. Well, to do that, we just simply figure out the group that they're in. Potassium obviously is in group 1A, so that's 1 valence electron. Oxygen is in 6A. Silicon is in 4A. Magnesium is in 2A. And iodine is in 7A. Okay, so with that information, we got 1, 6, 4, 2, and 7 valence electrons to work with. And you simply put the symbol out there, place the valence electrons, and you end up with something like that. Okay? That's it. Nothing complicated. And that just shows Lewis dot structure just is showing you how many valence electrons is each element has. Now keep in mind, all the chemistry, everything that's happening chemical-wise is occurring with the valence electrons. That's where all the action is, okay? That's where all the action is. All right, so let me clear this up. Now, so how do we, now notice that is a Lewis dot structure for atoms. Now what we're going to work with is to determine the Lewis dot structure for compounds. Okay, now we're doing Lewis dot structures. So the way we do this is we add up the total number of valence electrons that every atom brings to the molecule. So then you're always going to be told who is the central atom. So you write the central atom down, and then we just basically bond those other elements to the central atom and using a line to show that bond. Okay, keeping track of the valence, total number of valence electrons. Okay, because the thing to remember is whatever total number of valence electrons that you calculate, that is what you got to work with. You cannot magically just throw in more electrons if you need them, or you cannot magically just take them out. Okay, if you have a total of 6 valence electrons, you're going to make 6 work, one way or the other. And by making 6 works, six of them work, means that most of the time you can make single bonds and everything comes into play, you're good to go. Other times it seems like you're shorthanded. So that is where you start sharing electrons and creating double bonds and or triple bonds until as needed, okay? And maintaining that total number of valence electrons that you have to begin with. And so you're going through a check each time, making sure you maintain. And it's easy to lose electrons in the process. So that's why after every step, I count them, make sure I still got 10 or 8 or whatever I added up. And then I go to the next step, and then I count them again. And then at the end, I count them one more time, because I cannot add or subtract valence electrons, because that is governed by the atoms that you utilize. Second thing, when you start making double bonds and triple bonds, keep the octet rule in mind. Check the atoms, make sure the octet is fulfilled, with the exception of hydrogen. Hydrogen all the time, no questions asked, 2 electrons is done. Okay, so I can't add any more electrons. And obviously I can't subtract once it's made up, hydrogen bond has been made, it's done. All right, so those are the key points to remember. All right, so we surround the central atom with the other atoms that are in there, and then we draw single bonds to them and connect them. Now, as I just stated, we want to maintain the octet around all the atoms with the exception of hydrogen, whereas the duet. Okay, and then we do a final check, as I stated, to make sure you still have the same number of valence electrons that you calculated. And then on the atoms in the central atom, and the central atom only is what you need to do, is you check to see how many are bonded and how many are what we call unbonded or lone pairs. For example, we're going to go through this, but I'm going to give you the structure for water. We got oxygen as a central atom. We draw a line for hydrogen, a bond with hydrogen, 2 of them, okay? See right there, hydrogen with that line designates it's done. No more electrons on hydrogen. Its duet is full. Okay, those 2 electrons are being shared between the 2 hydrogens and the oxygen. And then we draw, I can either draw 2 dots or I can draw a line. I'm going to draw this, the left side as a line so you can see. Either one's correct. So that line represents 2 dots. Now, if you count the number of electrons around oxygen just itself, guess what? You got 8 electrons. And if you count the number of electrons on around hydrogen, you got 2 electrons. So the octet duet is fulfilled. Now we identify the bonding pair. Well, hydrogen, water has 2 bonding electrons. Okay, right there and right there. Then we identify the lone pair. Okay, and this is only for the central atom. Okay, and the lone pair has 2. So that is 1 and 2 pairs. So this water molecule on the oxygen has 2 bonding pairs, 2 lone pairs. What that does, once we identify, we then can utilize the central general formula. This is the general formula, ABE. A is always a central atom, so there's always 1A all the time, okay? B represents all of the atoms bonded to the central atom, regardless if they're the same or different. Right now, there are 2 hydrogens bonded to the central atom, so I put a subscript 2. This is the general formula. A is the central atom. B2 tells me there's 2 atoms bonded to the central atom. And E represents the number of lone pair. E represents a number lone pair on the central atom. We just counted 2 lone pair, LP here. And so we have A, B2, B subscript 2, E subscript 2. So that is our central atom. And you might say, okay, what does that tell me now? Once you identify the general formula for that molecule, then what comes into play is the shapes table. And remember, I asked you guys to download it so you can have access to it. And we came up with the central atom as A, B2, E2. And we go look in first column, and we find the general formula. And guess what? Here it is, A, where is it? Oh. There it is. We look for the general formula, A, B2, E2. And guess what that tells us? Here is the 3-dimensional model for the molecule of water. You got the central atom, which is oxygen, and then the 2 hydrogens. And then notice there's 2 dots, and it looks like, I don't know, it's just, this little line just represents an orbital, okay? And it just showing you those 2 electrons are on the central atom. Also, they're negative charged, so guess what? They're going to repel each other. And that results in this bond angle between the hydrogens to get smaller. So we call that geometry when there's a central atom with 2 lone pairs bonded to 2 atoms as bent. And that bond angle is less than 109.5. Our standard bond angle that you find a lot of our compounds out there in nature are what we call tetrahedral, in which you have a central atom and there's 4 atoms bonded to the central atom. Note, those bonds have electrons, negative charge. So they arrange themselves like magnets that are, you know, of the same charge, or the same north and north, south and south. They put themselves in a position where they maximize their distance away from each other. And that is the the maximum position of those bonds from each other, and that's a pretty standard configuration, which we call tetrahedral. That's kind of like our reference point for a lot of the bond angles, and that angle is 109.5. Okay, so let me clear this up. So that's why we identify that information here. Now, at that time, if we don't have sufficient number of bonds in our electrons and we cannot fulfill the octet, remember, I cannot add more magically electrons, or nor can I take them away. So that is where we start making double bonds. And that doesn't work, we make triple bonds. And we have some examples of how we're going to go about doing that. Okay. All right. So let's take the example of water. So you're given the formula H2O. Okay. And normally the central atom will have an underline, or the central atom will be bold in color. If it's not, then obviously you need to know who's the central atom, and that's where I come into play. Some maybe got missed, but the central atom here is oxygen. So we go and determine how many valence electrons everybody has. So there are 2 hydrogens. It is in group 1, and so there are 2 times 1 valence electrons. We go to group 6 and we find that's where oxygen's at. So if oxygen brings in 6 valence electrons. So total is 8 valence electrons you got to work with. Now, what I like to do is I just divide that by 2 because I know I'm gonna make a bond. And so I tend to like to work with pairs. So 8 valence electrons to me represent 4 pairs, okay? All right, so as we stated, oxygen's the central atom, so you can write the central atom down and then bond the other elements to the central atom. And like I stated, we have 2 hydrogens, so we can simply do that real quick. Guess what? That took care of 2 pair, right? So I can subtract 2 pair from what I got to work with. 4 pair is what you got to work with. You cannot add more because you need it, nor can you subtract. That is what you got. All right, so that took care of 2 pairs, so I got 2 pair left over. I got to put them someplace. Now, I cannot put them in hydrogen. Why? Because hydrogen now is happy with its duet. It's got a pair sharing with the oxygen. So both hydrogens, I can't put them on there. So the only logical place to put them is on the central atom. So I can very quickly just draw 2 lines right there. Okay. Now I go back and check. Do I still have 4 pair? I do. 2 of them are bonded to the hydrogen and 2 of them are on the oxygen. Okay, so I still have 4 pair. So those 2 that I just put on there got rid of the 4 pair I started off. So I went to 0. I should end up with 0 here. Okay, the hydrogen is happy with the duet and the oxygen is happy with the octet. 2 pair are lone pair and 2 pair are bonded pair. And so now I use the general formula again, like we just did. A is always a central atom. B represents the 2 hydrogens. And they could be anything. They don't have to be the same element, just as long as there's, in this case, there's 2 things bonded to oxygen. So I just put a subscript 2. And then I recognize that on the central atom, that's important. Only on the central atom do I have lone pair. So now I utilize the E, okay? So the general formula is A, B, I'm gonna put X, E, and let's call that Y, okay? Because X and Y are gonna vary. A is always gonna be the same, always 1. So that is my general formula. Then I go to the shapes table, look, oh, excuse me, I forgot something. There's 2 of them, there's 2 lone pair, okay? And so now I go to the central, to the shapes table, determine from the general formula, the shape of it and the geometry and the bond angle. Okay. All right.
I have a question.
Sure, go ahead.
The 2 on the E, that's with the ones with the oxygen, right?
That is correct. So let me put that back on here. Okay. And so the general formula is A, B, and it said X and Y. Okay. Now, B is the number of atoms on the central atom only. We don't care about anything else. Only. Okay. And E is the number of unbonded electron pairs on the central atom only. Okay, and we had 2 on there. I'm supposed to remember line there. So in this case, we got A, B2, and EQ. Okay. Because you can have a compound where you don't have any E. For example, we got carbon with 4 hydrogens. Well, that tells me that its general formula is A, B, and 4, B4. Okay. All right, so that E can vary. That B can also vary. But the point is that you have to identify once you come up with the structure, if that central atom has any lone pairs, because that affects the geometry quite a bit. Okay. So let me rehash. B and E only pertain to the central atom, which is A. All right. So like we said, we counted up the number of valence electrons, okay? And then we draw the 2 atoms that are bonded to the central atom, which are 2 hydrogens, okay? And then we went around and we checked to see our pairs, how many we got left, and then we looked for a place to put them. And we couldn't put them on the hydrogen because the hydrogen, its rule is the duet, okay? I think what sometimes is challenging is this bond right here. Okay? That bond are 2 electrons, and those 2 electrons are being shared with the hydrogen and with the oxygen. We're not going to talk about equal sharing or unequal sharing, but right now we're going to just say they're being shared, and therefore can be counted both toward the hydrogen and toward the oxygen. These electrons right here are not being shared. They are on the central atom. They're lone pair. They're just hanging out there, so to speak, on the lone pair. They're not doing anything with any other atom. And therefore, they're called non-bonding pair or lone pair. These that with the line are called bonding pair because they are bonded, physically bonded. Okay. All right. So maybe it's best to do a few more examples. Okay. Let's break it down. I cannot overemphasize the systematic approach to working with things. All right. Let's take a look at this one, HCN. We may not know what it is. That's okay. It's hydrogen cyanide, but we're just working what we got. Notice that everybody, all the 4 examples here have the central atom identified for you. So you know that's the central guy, then everybody else is bonded around it. All right, so step number 1, figure out how many valence electrons you have. So you got hydrogen, carbon, and nitrogen. And don't forget to account for the number of atoms of each one. So you only have one hydrogen. Okay, so that is one valence electron. Carbon, what group is carbon in?
Non-metals?
Pardon me?
Non-metals?
I know, but what group number is it in? How many valence electrons does it have? You're correct, it is a nonmetal.
4?
It's got 4 valence electrons because it's in group 4A. Okay, nitrogen, when it got one nitrogen, how many valence electrons does it have?
5?
5, exactly, because it's in group 5A. All right, so the total number of valence electrons that everybody brings to the table is 1 from hydrogen, 4 from carbon, and 5 from nitrogen. So that is what you got to work with. Can't add more, can't subtract more, okay? Because those are the 3 atoms you're working with. So we tally them up, and guess what? We got a total of 10 valence electrons, of which I like to just divide by 2. Now, you always will get a number that's divisible by 2. If you do your math and it does not divisible by 2, then something went amok, right? So you're always going to have a number divisible by 2. So that tells me that I got 5 pair to work with, or 10 individual electrons, okay? Now, that's the number of electrons. We go back to the formula. The central atom has been identified, and that is carbon. So we can write that down. We know now that being designated as central atom, the nitrogen and the hydrogen are bonded to the central atom. So I can very quickly draw a bond between carbon and nitrogen, and another bond between carbon and hydrogen. Okay, guess what? That took care of 2 pairs. So in my little grocery list of valence electron pairs, I can subtract 2 pair. So now what I got left over is 3 pair, okay? I got to put them someplace. Now, can I put them on hydrogen? Can I add a lone pair to the hydrogen? What do you guys think? Can I put a lone pair onto the hydrogen atom? And like by drawing a line like that? Or can I put all 3 of them around like that? What is wrong with that picture? Or is there anything wrong with that picture? With 4 electrons around hydrogen, what is drastically wrong with that picture?
It only has 1.
Yes, because what is the maximum number of electrons that hydrogen can have? 2. Okay, so by adding a line there and a line there and a line there, tells me it's got 4 pair of electrons around there, and I can't. That's not the rule for hydrogen. The rule is the duet: 2, 1 line, 1 hydrogen, and that's it. So that means that those 3 pair I got to work with have to go someplace. And so they can go on the carbon or they can go on the nitrogen, okay? Now, where you put them makes no difference. I like to start from the outside atoms and work my way in, okay? So since I can't put them in hydrogen, I can put them all on nitrogen. 1, 2, and 3. Count, that took care of 3 here. So now I got 0 pair to work with. So that's the number I got to keep track of to make sure I've not inadvertently lost the line here. So I still have 1, 2, 3, 4, 5 pairs of electrons, 5 lines. So I'm still good. All right. So all the valence electrons are out there. The central atom has been bonded to the other elements, which is hydrogen, nitrogen. Okay. Now I count the octet around the atoms. Okay, if we count, how many electrons are you counting around nitrogen? Just on nitrogen.
3.
Okay, total. Do I not have 1, 2, 3 lines, 4 lines around nitrogen by itself? Remember, this guy right here is being shared by nitrogen and carbon. So I can count them as 2 for nitrogen, and I can also count them as 2 for carbon. So right now, nitrogen has 2, 2, 4, 6, and 8. 2 more, 2 more, and 2 more electrons around it. Isn't that a total of 8? 2 plus 2 plus 2 plus 2, isn't that 8? Yes, it's 8. Yeah. And so there are, yeah, so right now, the way I wrote it, I got 8 electrons around nitrogen. All right. Now, how many are around carbon the way it's written right now? Total electrons.
4.
You got it? Exactly. There's only 4 electrons or 2 pair around carbon. So is carbon happy, so to speak?
Yeah.
What's the happy rule? What's that magical number? It's that same magical number if you ever shoot pool. What is that number? The black ball. Got a letter, starts with the letter E. What is the magical number of electrons that all atoms are striving to get around it?
8.
8. So does carbon have 80 electrons around it the way it's written?
No.
No, it's got 4, okay? It's got 4, only 4, so it's not happy. Remember, it's got 2 right here. I'm gonna put 2 there. It's got 2 there. There's 2 there, 2 there, and 2 there, all right? So at 2, 4, 6, 8, 10. Isn't that how many valence electrons we started off with? Yeah. Okay, right now, nitrogen has 8 electrons around it, so it's happy. Hydrogen has 2 electrons around it. It's happy because its rules are duet. Carbon only has 4. Okay, carbon's not happy. Okay, it is not in a stable state. So what we got to do, we got to make this such that, let me erase these numbers, we need to create, oh, where you go? There it is. We need to make it so that carbon is stable with 8 electrons around it. And we do that when you're in this situation, we take basically from Peter and share with Paul. You know, the old saying, right? And so we're going to take some of those electrons that are on nitrogen and create a double bond between carbon and nitrogen, okay? And you can arbitrarily pick any one. And I'm going to pick, I don't know, I'm going to go ahead and pick this one. And I'm going to draw on an arrow here to say that I'm going to take that lone pair and create a double bond. So I got C, H, H, and I'm going to keep those other ones in the same position so you can see we haven't lost track. Now go back and count how many bonds around the whole molecule. 1, 2, 3, 4, 5. I've not violated my rule of having 10 valence electrons. I still got 10 valence electrons or 5 pair, okay? Now go and check the octet around nitrogen. Nitrogen still has 8 electrons around it. I got 2 of them are now a double bond and 2 of them are lone pair, okay? Hydrogen's still happy with its 2, but carbon is not happy still. It's got 2, 4 over here shared with the nitrogen, and it's got 2 shared with the hydrogen. So it's got a total of 6. It is still missing 2 more. So what do? If we created a double bond and that didn't help, we create a triple bond. And let me get this here. There's a question. Hey, yeah, mandolin. Yeah, you're correct. Mandolin. All right, so what I do now, I'm going to create another bond or to create a final triple bond. So I'm going to take this lone pair on the nitrogen. I'm going to draw the arrow again to designate that I'm going to take it and create a triple bond. And so now I got C, triple bond. Remember, there's three types of bonds: single bond, double bond, and triple bond. Okay. Now, before I go any further, count the number of bonds around all the molecules. I still got one on hydrogen. Now I got 1, 2, 3, 4, 5. I still have 5 pair. I did not create anything. All I did was take a pair of electrons that were on one element, and I created a double bond so they share it with the other element. Okay, I still have 5 pair there. I still have total 10 valence electrons. I know sometimes mathematically you look at it and say, whoa, something's missing, but there really isn't nothing missing. I still have 10 pair total. Excuse me, 10 valence electrons or 5 pair. All right, now, final thing, check the octet or duet around everybody. Nitrogen still has 8 electrons. 3 of them are shared with carbon, excuse me, a triple bond, 3 pairs are shared with carbon. That's a total of 6 electrons are shared with carbon, and 1 of them is as a lone pair, okay? And carbon on the other side is sharing 1 pair with the hydrogen, and it has 8 around it. So now everybody octet rule has been fulfilled by creating double and triple bonds as needed to make sure that there's enough electrons around everybody to fulfill the octet. Okay, so that is the formula that we come up with. Now, from that step, go to the general formula. Remember A, B, X, E, Y. Well, we got A, always A, okay? B, well, was bonded around the central atom, 2, okay? E, we don't have an E here. There's no lone pair on the central atom, which is carbon, okay? So there's no E. So the general formula for this molecule is AB2, okay? So now, with that information, go to the shapes table and look for AB2 in the table, and it happens to be the first entry right here, okay? And that is the molecular geometry. This could be nitrogen right there. This could be carbon in the central, and then hydrogen over here, okay? And you can see that bond angle between the nitrogen and the hydrogen is 180 degrees. Its shape is a linear shape. That is the shape for that molecule. And that's how we come up with the geometry for this particular molecule, hydrogen cyanide, HCN. That triple bond forced everything to become linear in shape. All right. Let's go back. So with that in mind, that is the formula, exactly what we just went through, okay? Now, I kept my solid line on that nitrogen. That's a lone pair on the nitrogen. That's not a lone pair on the central atom, which is carbon, okay? I want you to distinguish that. Be aware of that. Yes, this is a lone pair, but it's not a lone pair on carbon. So that's why you will not see an E. This general formula is AB2, okay? Now, let's look at this one. This is carbon with hydrogen and 3 fluorides around it. This would be a fun one. Okay, look at let's look at carbon. Carbon's a central atom. How many valence electrons in carbon again? There's only 1, So 1 times 4 equals 4, right? It's in group 4. Hydrogen. Hydrogen, there's only one hydrogen, and there's one valence electron from hydrogen. So we only got one valence electron coming from hydrogen. I'm making my little list of valence electrons. Sometimes, like the first example, very short and easy. Sometimes you have to kind of really check your math here because we got fluoride now. Now we got 7 of them. Oh, excuse me, what am I saying, 7? I already gave you what the next answer is. I meant to say 3. How many valence electrons does each fluoride bring to the table? What group is it in? Obviously 7, right? I told you that. So I got a total of 21 valence electrons coming from the fluorides. So I tally up 4, 5, 6. Right? Excuse me, 26. I got a total of 26 valence electrons to work with. All right, and guess what? That's numbers divisible by 3. So that tells me I got 13 pair, which is a number I like to work with. Trying to keep track of 26 dots can be a little can drive you a little crazy. So I like the pair so I can just draw a line. Okay. All right. Carbon is the central atom, so we can very quickly draw carbon. Now, there is one hydrogen bonded to the central atom, so we can draw that quickly. And then there are 3 fluorides bonded around the central atom, so we can draw those quickly also. Okay, so with that, we have taken care of, you start off with 13 pair. We've taken care of 4. Okay, doesn't that mean we got 19 pair to work with left over? All right, now, we just talked about hydrogen. Hydrogen, we can't add any more electrons to that because it's happy. It's got one line there with carbon, it's shared 2 electrons, it's happy. How many bonds are around carbon? The way I wrote it. Anybody tell me? How many bonds are around carbon the way I wrote it? Don't I have 4? Each one has 2 electrons. So how many electrons are around carbon as I wrote it? Anybody want to take a chance at it? If I got 4 bonds and there's 2 per bond, how many electrons do I have around carbon?
8.
8, right. So can I add any more around carbon? No. It's octets happy. We're done with carbon. And so you may ask, okay, I got 9 left though. Where am I going to put them? Well, you can't put them on hydrogen. You can't put any more on carbon. Where must they go? They have to go around the fluorides. And so I very quickly put a line around each fluoride, 3 of them actually. Why 3? Because I go 1, 2, 3. It's got 1 already. Isn't that 8 electrons already there? Right, so this fluoride I just wrote on is done. I go to the next one. 1, 2, and 3. Again, I got 4 lines around that fluoride. It's done. Okay, each line represents 2 electrons. So now I go, I took care of what? 6, right? 6 pairs. So I got 3 pair left over. The only place it can go is on the other fluorides. So go 1, 2, and 3. And that took care of the last pair. So now I got 0 pair to work with. I start off with 13 pair. I go back and check. Do I still have 13 pair? Because you can easily lose a line as you're building this. So go back and check. I got 6 around the fluorides, right? 6. 1, 2, 1, 2, excuse me. 9, what am I saying 6? There's 9 around the fluorides as single bonds. That's 9. And then the bonds inside the central atom, there's 4. So 9 plus 4, guess what? 13. Okay. There's, let me draw a different color if you don't see it. Okay. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Isn't that what we calculated? We should have 13 pair or 26 valence electrons, 26 single pair. Now, a lot of people can do this, and this is efficient if you want to do that. But that's a lot of lines, dots, I should say. That's why I like the lines, because I don't have to worry about losing dots. I just have to worry about losing lines. Okay, this, the way I wrote it with all dots is the same thing as I wrote it with the lines. Okay, because each line represents 2 electrons. All right, so I checked to make sure the valence electrons are the same, and they are 13. And so now that's my formula. Okay. And so now I know, let me clear this up a little bit. It looks like it's getting a little too messy. Let me do this and I'll redraw it. Because the next step is to determine the geometry. And so this is what I had. This is, by the way, is called trifluoromethane. These are fluorinated hydrocarbons that used to play havoc, still do, on our ozone layer up in the atmosphere. So that's our general formula. I mean, our formula that we came up, our general formula would be A is the central atom, B are the fluorides, which are 3 of them and 1 hydrogen. So I got B4, A, B4. We don't have an E because there's no lone pair in the central atom. So that's our general formula, AB4. At that time, this time we go to the shapes table, and that's, we look for AB4, and lo and behold, there it is, right there. There's AB4, and that is the shape, the 3-dimensional shape. You know, we do live in a 3-dimensional world, so this does a fairly decent job of trying to show you how it is structurally 3-dimensionally. The main point about this is called tetrahedral, that geometry, and that is the bond angle between the species is 100, between the fluorides and the hydrogen are 109.5. This is the general geometry that nature uses quite a bit out there, okay? Especially with organic compounds or biological compounds. All right. Okay, so that is the formula for the trifluoromethane, is the name of it. Okay, we've got a couple more here. Okay, so we have carbon dioxide. All right, carbon, as we've done with the previous examples, there's only 1 carbon here, and it brings 4 valence electrons, so it's 4 valence electrons. Okay. Oxygen, there's 2 oxygens. Now, how many valence electrons does each oxygen bring? You can tell me how many valence electrons does each oxygen bring to the table here?
6.
You got it. And that's because, again, it's in group 6A, Roman numeral 6A. So that means I got 12, right? 2 times 6, 12. So I have a total of 16 valence electrons. Is that correct? Hold on a second. Okay, how's my math looking? Did I make a mistake anywhere? I got 1 from carbon. I got 6 valence electrons for each oxygen. There's 2 of them. Okay, so that's a total of 16. So how many pair do I have?
8.
You got it. So I got 8 pair. Now, like I said, I choose to work with 8 pair. For me, it's just much easier. You want to choose to use 16 dots, that's fine too, whatever works for you. Okay, so we got 8 pair to work with. And here, carbon as usual is the central atom. So we can very quickly write carbon in the center. And then there's 2 oxygens, so we can quickly, as before, bond our 2 elements that are bonded to the central atom. So we write them with the line showing that there's a bond. So what that does is that takes care of 2 pair. So what do I got left? I got 6 pair to work with. Okay. Now, where do I put them? Well, good thing is you don't have any hydrogen to worry about. You only have 2, right? You only have carbon and oxygen. So you can put them anywhere you want. I prefer to go in the outside atoms and work in. Okay, so you do it what works best for you. Eventually, it's all going to be the same at the end of the day, as they say. Okay, so I'm going to put them around oxygen. So I go 1, 2, and 3, and I stop there because there's 4 around oxygen. That gives me the octet. I'm done. I move on to the other one. That took care of 3, so now I put the other 3 down. Okay, and I put that around the oxygen. And there are 4 around oxygen here for the right side oxygen. So there's 4 pairs on each oxygen for a total of 8 electrons. So the octet is happy for the oxygens. How many electrons are around the carbon though?
4.
4 exactly, or 2 pair. And so you can see that carbon is not happy, all right, because it needs 4 more. Now, can we magically pull 4 more electrons out of space and put them in there? No, we can't, because we have a total of 8 to work with. That's it. I can't add more, can't subtract more. And I go back and check to make sure that I got a total of 8 pair. So I got 1, 2, 3, 4, 5, 6, 7, 8. I got 8 pair. I didn't lose anything. Okay. The oxygens are good. The carbon is not. And like we did up here, what do? We borrowed from Peter to share with Paul. And so we're going to borrow a pair of electrons from each oxygen. And I'm just simply going to draw a line like that. Which ones you select makes no difference. Okay, and I'm going to create double bonds around carbon and oxygen. So I end up with carbon, double bond oxygen, and then my 2 lines on the oxygen. And then on the other side, I got another double bond. Okay, go back and check, make sure you still have 8 pair. And I do have 8 pair. If you count the lines around this molecule here, there are 8 pairs of electrons around the whole thing. Go back and check your octet. Oxygen on the right side still has 8, no problem. There's 2 lone pairs and 2 that are shared with the carbon. The oxygen on the left also has 8, 2 lone pair and 2 bonded. And if we look at the carbon in the center, it has 2 double bonds, 1 on each side. So that's a total of 8 electrons. So therefore, folks, that molecule the way we wrote it, that is the structure as written for carbon dioxide. And our general formula would be AB2. Okay, AB2. And so we go to the shapes table. We look for AB2, and just like the first example, there's a general formula, the first entry. There's a picture of the geometry, and its name is called linear. And so you can see here that we have the carbon in the middle, and then the two oxygens over here. Just like previously, we have hydrogen, carbon, and nitrogen. Remember that one? Same shape. So we're going to be learning that a lot of molecules have very same shape. Also, we're going to learn that this particular geometry of carbon dioxide explains why it is what we call a non-polar species. It won't dissolve in water very well. If, you might say, well, wait a minute, I got carbonated drinks all the time. Yeah, if you take that soda bottle, shake it up, what happens? The carbon dioxide is pulled away. If it truly was soluble, you could shake that thing all day long and that carbon dioxide wouldn't go away. Yes, it's dissolved in water, but it's not soluble. Unlike sodium chloride, you put that in water and you shake it, nothing's going to fly out because sodium chloride is truly soluble in water. But it's that way because of its geometry. And we're going to learn about, and that's related to the electronegativity of oxygen and carbon, of the elements, and how they interact with each other to form a particular type of bond, okay? But it's all tied into this and how it's put together. Right? We're slowly building up, hopefully, a better understanding about chemistry and how it interacts and reacts with our environment. Anyway, we got this, and there's the formula. Linear, okay? And there you go. All right, let's do one more. The last one, we have nitrogen and hydrogen. All right, so systematic approach. I know sometimes it might get a little boring, but I'm telling you, you do a systematic approach to any problem, you'll figure it out. So we got one nitrogen, okay? And nitrogen is in group 5. And so it brings 5 valence electrons to the table. Hydrogen, there's 3 of them, and each one brings 1 valence electron. Therefore, we have a total of 3 valence electrons coming from all the hydrogens. That's the key here. Sometimes students forget is, you see a hydrogen and you only put 1, but keep in mind, you got to keep count for all of the hydrogens in your molecule, and there's 3 of them. So that brings in 3 valence electrons. That's a total of 8 valence electrons, or AK also known as 4 pair to work with. 4 pair. Okay, nitrogen is the central atom, so we can very quickly write nitrogen down, and then there's 3 hydrogens bonded to the central atom, so we can draw the bonds to the 3 hydrogens, okay? So that took care of 3 pair. So that leaves 1 pair left. Well, again, like we talked about up here, I can't add that 1 pair to any of those hydrogens because the duet has been fulfilled for each and every one of those hydrogens. So the only place I can put that 1 pair left is directly on the nitrogen. I'm just going to put 2 dots here to show you that. Okay. And so go back and count how many pair do we have. We got a total of 4 pair. Okay, we took care of that one, so I had 0 pair to work with left over. And so we got 4 pairs, so we did not lose any pair in the process here. All right. Once you're done with that, you write the general formula. Obviously, A is there. B, again, what is B? What do you think B will be here for this particular compound? What's the subscript for B here?
Would be 4.
Oh, no. How many atoms? How many atoms are around the central atom? Okay, what's that number right there?
3.
You got it. Okay. That's not an atom here that I put in the central atom. Those are electrons. So in this case, it has one lone pair, one E. Okay, that's the E part. Remember that. The B are actual atoms bonded to the central atom. They could be the same atoms or they could be different. Makes no difference. It's just the total number of atoms bonded to the central atom. So our general formula is AB3E. Okay. So then we just go to the shapes table and look for AB3E, which is right there. Okay. There's AB3E. And there is the formula. So this could be thought of, you got the nitrogen in the center, and then the 3 hydrogens bonded to the central atom. Notice they got a bond there. And then that lone pair is sitting on the central atom. In that particular case, you would think, 4 like tetrahedral. But here in this case, what's happening here, there's something bonded here. There's some atom bonded to the central atom. The lone pair is being shared. Over here, there's the lone pair all by itself. And guess what? This little semicircle thing here is trying to show you that is that orbit that takes up a lot of space. Because those 2 electrons, remember, have negative charge and they're going to repel each other. And when they do that, that bond angle gets pushed in, just like an umbrella. You think of an umbrella, it gets powered by wind. It inverts itself, it gets pushed in. So that bond angle becomes much less than the standard 109.5, okay? And that is because the lone pair. The lone pair on the central atoms have a lot to do with how compounds react, how they behave, and a lot of the properties. A lot more to say about that central or the lone pair in the central atom, because every time we figure out that there's a lone pair in the central atom, the thing that we can very quickly deduce is it is a very polar molecule, meaning it's very polar in water. Okay, it should be it should dissolve in water. It's basically what I can say. Its name is trigonopyramid. Okay, much different than the tetrahedral. All right, and that, by the way, folks, is the formula for something you may have smelled before as ammonia. Okay, ammonia. All right, well, I see let me see, you got one more. Let me do one more. Getting close to the end here. Now, we tried this, we went through HCM. And this is just an example of what we just talked to, HCM. And then we drew the 2 bonds of hydrogen and nitrogen, okay? We checked for the octet. And then we created double and triple bonds, okay? We eventually create that structure there. And then we went through the shapes table to determine its particular geometry. All right, now we're going to not do it now, but next time we're going to talk about this Lewis dot structure for polyatomic ions. What exactly is that? Well, I want you to take your periodic table and look down here in the bottom left corner of the periodic table. Okay, and it states in there a name, most common polyatomic ions. Right now, These have charges. These are ions, just like we talk about elements or atoms that lose and gain electrons to form ions. Well, there are examples of what are called polyatomic ions, which are more than one atom, polyatomic, that overall have a charge of either a negative or a positive. Okay, they are also anions or cations. We're only going to be working with one cation, it's the ammonium in the upper left corner here, but all the other ones have a charge. Notice they have a upper superscript negative, either a -1 or a -2. Okay, and you may be familiar with these. You may have used them someplace bicarbonate, sodium bicarbonate. There's the structure, it's HCO3, and if you got sodium, it'd be sodium HCO3. So sodium bicarbonate, aka baking soda. All right. So we're going to come up with the Lewis dot structure for these, just like we did for neutral species. These are charged species, they're ions. And we're the same process. The only difference is this: we have to be aware of the charge, because we either, if it's positive or negative, we either have to subtract or add to the valence electron count that we calculate. Okay, so we will do that next time. And we'll stop it here on slide 21. And definitely for sure, next time on Tuesday, we'll be done with chapter 31. Excuse me, chapter 7, page 31. All right. Let's stop.